I'm Sajjad Fazeli from Industrial and System Engineering Department of Wayne State University. Dr. Saravanan, Dr. Chinam, and Dr. Murat were supervising me during this research project. My research about the two-stage stochastic choice modeling approach for electric vehicle charging station network design in urban communities. There are many reasons that why we should invest on electric vehicles. They produce less pollution, less noise. They are very cost effective and they have low maintenance cost. In 2017, more than 3 million of electric vehicles were sold around the world. And it is estimated that at least 300 public charging stations should be, is needed per million people. And in the US, half of the population lives in a market with charging a station at least 70% below this benchmark. Many studies proven that public charging infrastructures and workplaces are the most important factors in adoption of electric vehicles. Electric chargers are different in terms of power and charging prices, and different people have different preference or sensitivity toward these different types of electric chargers. As you can see, we have generally we have three types of charger. Level 1 is very slow charging and it's very cheap. Level 2, semi-fast charging. It's a little bit more expensive, and fast charging, which is expensive, but it's very fast. So it's very important to capture the EV drivers' behavior charging pattern, which can lead to a better distribution of the budget to the charging stations, more adoption of EVs, and also more accessibility to charging stations. I will quickly review the literature review from two perspectives. The first one is a stochastic approach. Although there are many studies in other fields that study this uncertainty models, but in terms of electric charging station network, there are only few studies that incorporate uncertainty in their models. For example, Pan et al., they developed a two-stage stochastic model for locating the charging stations. They considered uncertainty of demand into battery loads and generation of renewable power sources. Hosseini et al., they incorporated uncertainty in traffic flow, and they formulated two-stage stochastic modeling for both capacitated and uncapacitated version of EV charging stations. Also, Arsalan et al., they consider the EVCS problem as an extension of flow refueling location problem. Another approach is choice modeling approach. Usually, choice models are based on the assumption of maximizing the utility of the decision maker's behavior. In terms of charging stations, there are few studies. Zhu et al., they developed a mixed logic model. They considered many factors that affect the battery electric vehicle users in Japan. Also, Liu et al., they implemented two-level programming to locate multiple levels of charging facilities, including wireless charging and consider consumers' charging and routing choices. Also, Wolbert considered the policy effect on charging behavior and EV adoption using the choice models. Okay, I will talk about our solution approach. We first collected the data from three main sources. First is SEMCOG. It's a planning agency in southeastern Michigan. The second one is the National Household Travel Survey, and the third one for the literature. We then, in pre-processing, we used Monte Carlo sampling technique, basically the simulation approach, to generate our demand. Then, based on the data from the demand generation, we calculate the utility of each driver at each location for each type of charging level. Then we aggregated those utilities and feed it into the mathematical model. We used two-stage stochastic model, actually which we embedded the choice modeling into these two-stage stochastic model. From the methodology point of view, we implemented the sample average approximation to estimate the less number of scenarios. I will talk about it later. And also we implemented the L-shaped decomposition method to solve the problem efficiently. Also, to demonstrate the efficacy of the model, we use a case study we consider part of the Detroit area. And at the end, we will provide some computational insight, computational result, and some insight from the access, utilization, and pricing perspective. So our final goal is to provide a framework which can determine the location, capacity, and type of the charger at each charging location. So there are many uncertainties that affect the demand for charging stations. Most of them have the uncertain natures. The first one is annual daily traffic. We use the SEMCOG data and uniform distribution for generating the data here. The second one is the dwell time. We consider 6 different type of destination or activities such as work, social, shopping, school, meal, and family. And this data gathered from the literature. And also this is the average dwell time of different activity in community. The third one is arrival time. Again, from the same sources, we have the arrival time at each time of the day for each activity and for weekend and weekdays. Also, we use we actually consider the state of charge of electric vehicle when they arrive at parking location. And it turns out this follows the normal distribution with mean of 30% charge. It's also gathered from the literature. And another important thing is the willingness to walk off the commuters. We consider their willingness using the decay function, which is provided again by the literature. I will talk about it later. And the last one is the BEV market share. We consider 2% market share based on the data gathered from the Department of Transportation. Okay, so from the choice modeling perspective view, based on web survey, when et al. They analyze the charging choices of BEV owner in different parts of the US. Usually choice models compute the volume from the demand sources to selected locations. To compute this volume, we need the utility function. Utility function is estimated by some variables. They used some variables and they estimated those variables using mixed logic choice model. The variables are price, charging cost, cost at home, dwell time, power level, level 1, level 2, and level 3, range charge, remain short, and the last one I will talk about it in the next slide. Some of these are constant, but some of them are interactive variables, which I explain it now. For example, range charge at a station, it means that the amount of charge that electric vehicle can get during the charging period in each station, which calculated as minimum of power times, dwell time, or energy consumption of electric vehicle, and the max range, which we considered 75 miles for BEV for our study, and the current range, which is estimated by state of the charge. The other factor is the charging cost, is the price of each charging level times the dwell time. Dwell time is the stay of duration of stay. In Michigan, we consider 3 prices. For level 1 is 30 cents per hour. on average. Level 2 is 1.5 per hour, and level 3 is almost $21 per hour. So it's pretty expensive. Remain charge is the remain charge after the commuter or driver reach to home after charging the electric vehicle at charging a station. It's a long formulation, but we also have the distance to home. We consider 50 cities around the Detroit. We're using the distribution of the data gathered from the same cog. But then we generate a distribution for that, and we randomly generate the origin for our commuters. Also, cost at home is based on range to be charged at home and energy consumption and electricity price at home, which is in Michigan is around 14 cents per hour. Also, the last factor or variable is enough to next charging opportunity. It's binary variable since we are considering the midtown area. This is more valuable for highways, so we consider as 0 in our problem. So for our mathematical model, we have different set of parking lots, set of timing slots, set of buildings as final destination of the commuters, set of charger types, level 1, level 2, and level 3, set of possible parking lots within the driver's walking distance based on that decay function, set of scenarios, and we have some parameters: installation cost of chargers, capacity at each location, total amount of budget, demand of each building. Again, we have another types of demand for based on the walking distance. Then we have the aggregated utility of EV drivers for each charger type at each location. Since we have two-stage stochastic model, the first stage variable are decide the location of parking lots and whether we select them or not, and then number of charging types at each station or at each parking lot. Second stage variable calculate the proportion of demand building B in time period for charging type N in a scenario omega. So this is our two-stage stochastic model. The first stage, we maximize the expected access to the charging stations. Then we constraint 2 and 3, they determine the capacity, charging capacity at each parking lot. And constraint 4, it's a budget constraint. And the second stage, in the second stage, we try to maximize the coverage of potential EV traffic flow based on decision made in the first stage for each scenario. Constraint 7 shows some kind of supply-demand balance restriction or capacity restriction. Constraint 8 is the choice model constraint. And constraint 9 and constraint 10 are duplication constraint. We don't want one driver go to 2 parking locations based on the walking distance preference. So since the constraint 8 is a nonlinear constraint, so we have to linearize that constraint. We use the McCormick linearization or McCormick envelope. We replace the constraint 8 with 4 constraints, constraint 12, 13, 14, and 15. I'm not going into the details for this one. And to demonstrate the efficacy of the proposed approach, we investigate the case study within a midtown Detroit area, which has lots of different types of building in terms of activity, hospitals, offices, schools, and museums. We candidated 31 parking lots at a potential location for installing charging stations. From the methodology point of view, first we consider sample average approximation. Unless there are a few number of scenarios, we cannot solve the two-stage stochastic modeling to optimality. But in the literature, it is shown that we can approximate the optimal solution of the stochastic problem with much smaller number of scenarios with sampling techniques. So we use the sample average approximation. And the main 3 steps of sample average approximation is estimating upper bound. We generate m independent sample set of scenarios and with n sizes, and we estimate the upper bound for the minimization problem, and we estimate the lower bound based on the fixed solution from the first stage with a very large number of scenarios for the estimating the lower bound. Then we calculate the difference between upper bound and lower bound and report it as a gap, and also we report the standard deviation based on the formulation you can see here. So for the SAE setup, we used m sample and m prime is 1,000, consider 1,000. We have different number of scenarios in the first column, different number of parking locations. And here we have the upper bound, lower bound, and gap between the sample average approximation, and also the standard deviation. We thought that maybe 40 scenarios is good for our computational result based on the SAA. Then to solve the problem faster, or we used the decomposition algorithm. We used L-shaped decomposition algorithm, which is an extension of Bender's decomposition. Generally, we decompose the problem to the first stage or master problem and second stage or sub-problem. The information iterates between first stage and 2 stage, and we calculate the upper bound and lower bound, and we add the duality cut to the master problem. We consider 2 types of L-shaped decomposition, single cut. In each iteration, we add 1 cut to the master problem, and multi-cut. For each scenario, we add 1 cut for each scenario. So if we have 40 scenarios, we add 40 cuts to the master problem in each iteration. Then we solve the problem until the lower bound and upper bound reach to certain predetermined gap. So the model specification in terms of number of constraints and variables, with 40 scenarios, you can see that the number of constraint variables can reach to around 8 million. And we have first stage variable, first stage constraint, second stage variable and constraint, and number of non-zeros in our problem. So the result of the decomposition, and also DEP is deterministic equivalent problem, just solving the problem with solver, not using the decomposition technique. And we report the gap, and we limit the running time to 1 hour. And in most cases, multi-cut L-shaped decomposition outperform the other 2 approach, especially the DEP one. For when we increase the number of scenario, the Groovy software cannot even return any gap for our problem in 1 hour time limit. Okay, so we perform a case study. We consider 40 scenarios, 10 parking lots, 2% market share, 152 parking location, when we used uniform distribution for average annual daily traffic between 10,000 and 40,000. This is we consider these 10 parking location in the study area. This is the heat map of the study area when the commuters come to the midtown. And the first result is related to accessibility. With increasing budget, we can increase the accessibility to certain level. And we also report the utilization of level 1 charger and level 2. Level 2 charger has higher utilization here in most of the cases. Again, for level 1 and level 2, we report here the average utilization for some of the parkings in different time periods or time slots. And this is very interesting for charging station provider especially. when they want to see the utilization rate. This is for level 2 charger. And this is the total number of chargers with different amount of budget of level 1 and level 2 labeled by accessibility. As we increase the budget, the ratio of level 2 charger is, the ratio becomes bigger in favor of the level 2. Another interesting insight is the total, the average of utilization for level 1 and level 2 in different time slots with different amount of budget. And we can see in each at what level of budget we can get higher utilization of charging levels. So you may have noticed that we didn't see any results for level 3 or fast charger, and that's because the fast charger is very expensive for the user based on the data we gathered. Here we just fix the level 1 and level 2 price and just change the level 3 price to see at what level people are willing to use fast charging at urban communities. So the green bar is related to fast charging. The orange one is to level 2, and the blue one is level 1. This is the aggregated utility for all the users at different parking locations. So this is when the price of level 3 is $9 per hour. This is $6. This is $4. At $4, it's almost people are using or have preference to use level 3, and at price level, actually this price for $3 per hour, they prefer level 3 over other charging levels. So at the end, the contribution of our work, we provide a framework, and we design a community-aware charging network for electric vehicles. We use two-stage stochastic programming model to determine the location, capacity, and type of public EV charging stations. To maximize access to charging stations, we considered drivers' behavior using choice modeling, which is embedded into two-stage stochastic model. We considered many sources of uncertainty in our problem, and we adopted a sample average approximation to determine the efficient number of scenarios. And we implemented the decomposition technique to solve the problem efficiently. And also we perform a case study and post-analysis framework. Also, a paper was published last year in IEEE Transactional Intelligent Transportation System Journal. Thank you.